At first glance, this looks like noise, just random points. But if I keep going, something extraordinary happens. This is Sierpinski carpet, and it emerged from nothing but chance. So if every choice is random, why don't we just get a noise? Why this intricate fractal with holes? Where does the order come from? The answer lies in a simple mathematical process known as the chaos game. Consider a square with its corners labeled as ABCD and edge centers as AFGH. We begin by choosing any random starting point, call it point 0. Then we roll an 8-sided die. The outcomes correspond to our 8 attractor points, that are our 4 corners and 4 edge centers. Based on the die, we select one of these points. Then we move exactly 2/3 of the way from our current position toward the chosen point. We mark this new location as point 1. Now we repeat. Roll the die again, choose the corresponding point, move 2/3 from point 1 to this new target and mark point 2. We continue this process thousands of times. And remarkably, as the number of points grows, the Sierpinski carpet emerges from this simple rule applied to random choices. Let us dissect the chaos game one move at a time. Recall that we start by choosing an initial point anywhere inside the square. After this, suppose we roll a C on the die. The fascinating thing about this case is that no matter where we choose our initial point, the second point is always restricted to lie in the shaded square in the upper right corner. To convince yourself this is true, you might want to try this by choosing bunch of initial points and move 2/3 way to C and find that these all points always lie in the shaded square. If we roll F on the die, the second point is restricted to lie in the square corresponding to its label. Same is true for all points. Concluding, no matter what the initial point is and no matter what the die rolls, the second point lies in these shaded squares only. Thus, it is excluded from lying in the central square. In general, on each step, the area where our new point may lie gets restricted in a particular fashion. For instance, after rolling C on the die, suppose we roll D. These are the possibilities of second point, as we know. Now, the third point is restricted to lie in the square corresponding to corner D, which indeed lies in the square D, which we all know, but stays away from the central square of D this time. We will see this is true for all combinations of first roll and second roll with this animation. So, what do we observe? On first roll, the point is excluded to lie in the central big square, and on the second roll, the point is now excluded to lie in the mini squares surrounding central square. Surprisingly, this is the exact same process which we use to form an ideal Sierpinski carpet. And thus, no wonder now why this game leads to a fractal. And to be mathematically precise, this is not an ideal carpet. Why? Just think, if we choose the very first point in the central square itself, that point should not exist in a true Sierpinski carpet. The ideal one has the central square completely removed at every scale. But here's what truly fascinating. The game still leads to a shape so remarkably close to the Sierpinski carpet that to our eyes they are identical. Even with randomness in every choice, even with that theoretical imperfection, mathematics guides chaos towards order. This is beauty of mathematics, and I think these things are one of those things which spark up curiosity in learning mathematics. They remind us that mathematics is not just about rigid rules, it's about uncovering the hidden music in what seems like noise. Wait, this is not over yet. Did I say something about the sense of randomness in all this? Well, I didn't, but I should have. Because here's the mind blowing part: create this perfect order, randomness is a necessity. Let's prove it. Suppose we remove randomness. What if we chose corners in a strict order? A, B, C, D, repeat. Let's try. Orbit becomes trapped in a cycle. It never wanders across the entire square. We're stuck. Without randomness, we never obtain the Sierpinski carpet. But with randomness, the order in which we visit points is unpredictable, yet the destination is mathematically guaranteed. It's as if randomness is the key that unlocks the door to order. There's much more to explore: fractional dimensions, infinite perimeter in finite space, mathematical monsters that are beautiful, but that's a topic for another video. My main hope is that you've developed some curiosity about fractals, about how mathematics finds patterns in what seems chaotic,